The queen is surrounded, not in the ceremonial protective way that the word surrounded might imply when applied to royalty. In the other way, the workers have formed a tight ball around her, hundreds of bees clustered so densely that she cannot move, cannot breathe properly, cannot escape. They are vibrating. The ball is generating heat, and that heat is the mechanism. The workers are cooking her alive. This is called balling, and it is one of the most dramatic and most misunderstood events in beekeeping and apiary management. When beekeepers first encounter it, the instinct is to intervene, to break up the cluster, to rescue the queen, to restore order. The impulse is completely understandable and almost always wrong. The workers know something. They have assessed the queen and reached a specific conclusion, distributed across thousands of individual assessments, coordinated through chemical signaling rather than any central decision-making authority, and they have collectively determined that this particular queen needs to be replaced. The mechanism is brutal. The logic is impeccable. Understanding why bees turn against their queen, under what conditions the workers' assessment of queen quality flips from support to elimination, what signals trigger the coordinated replacement response, and what this reveals about the extraordinary social intelligence of bee colonies takes you into some of the most fascinating territory in all of behavioral biology and evolutionary ecology. And it has more relevance to the human experience than you might initially expect. Start with what the queen actually provides the colony, because understanding what she provides is the foundation for understanding what happens when she stops providing it. The queen's contribution to colony function falls into two specific categories: reproductive output and chemical signaling. The reproductive output is the visible part. She can lay 2,000 eggs per day at peak production, a rate that sustains the colony's workforce against the continuous attrition of worker mortality. Each worker bee lives approximately 6 weeks during the active summer season, which means the colony's population is turning over almost completely every 6 weeks. Without continuous high-volume egg production from the queen, the workforce declines, the colony weakens, and eventually collapses. The chemical signaling component is less visible but equally critical. Queen mandibular pheromone, a complex blend of fatty acids and aromatic compounds produced in the queen's mandibular glands, is the primary information molecule that organizes colony social behavior. This pheromone suppresses worker reproductive development, preventing the development of worker ovaries and maintaining worker sterility. It inhibits workers from initiating queen-rearing processes as long as the existing queen's signal is strong and consistent. It marks the queen as present and functional, providing continuous chemical confirmation that the colony's reproductive specialist is doing her job. Workers assess queen quality continuously through multiple sensory channels. They can detect pheromone concentration and composition through their antennae, which are extraordinarily sensitive chemical detectors. They can assess egg-laying rate through direct inspection of comb cells. They can evaluate the queen's physical condition through contact interactions during grooming and trophallaxis. And they share this assessment information across the colony through chemical signals and behavioral cues that propagate through the thousands of bees that compose the colony's workforce. When the queen's pheromone production declines, as it does when she ages, when she is injured, when her reproductive system begins failing, or when her egg-laying rate falls below the threshold the colony requires to maintain its workforce, the worker's assessment begins to shift. The chemical signal that has been maintaining worker sterility and suppressing queen-rearing behavior weakens. Workers that have been measuring this signal continuously detect the change. The colony's collective response begins to organize. The specific process by which workers identify a failing queen is worth examining in detail because it reveals the specific form of distributed intelligence that makes bee colony management so extraordinary. No single worker performs a comprehensive assessment of the queen. No individual bee has both the information and the authority to make the replacement decision alone. Instead, the assessment is distributed across the colony's population in a way that integrates information from thousands of individuals. each of whom has access to a specific subset of the relevant data and produces a colony-level behavioral response that reflects the aggregate of those individual assessments. Workers near the queen experience higher concentrations of queen mandibular pheromone than workers on the colony's periphery. Workers in the brood nest see the pattern of egg laying directly, the specific distribution of eggs across cells, the density of egg presence, the freshness of the eggs. And this information is available to any worker that inspects the brood nest. Workers involved in trophallaxis with the queen have direct contact with her surface chemistry and can detect changes in her chemical profile that indicate physiological changes. The sharing of this information across the colony occurs through trophallaxis itself, the exchange of fluids between bees that transfers chemical information along with nutrients, and through the specific behavioral patterns that workers adopt in response to changes in queen quality signals. Workers that detect declining queen pheromone begin spending more time in brood nest inspection, more time in queen rearing preparation behaviors, more time in the specific antennation behaviors associated with assessment of potential queen cells. This shift in worker behavior is itself a signal that propagates through the colony. Other workers observing the behavioral changes of assessment-focused workers adjust their own behavior in response. The colony's collective behavioral state shifts progressively from normal maintenance mode toward queen replacement mode, driven not by any centralized command, but by the distributed propagation of assessment information through individual behavior changes. The result is what behavioral biologists call a superorganism decision, a colony-level behavioral outcome that no individual could have produced, but that emerges from the specific interaction patterns of thousands of individuals, each responding to local information. The decision to replace the queen is made by the colony as a whole through this distributed process, and the specific timing of that decision reflects the integrated assessment of queen quality across all of the information channels that the colony's workforce has access to. Now address the specific conditions that most frequently trigger queen replacement, because the balling event described at the opening is not the only mechanism through which workers turn against their queen. It is the most dramatic, but it emerges from a specific subset of situations that trigger it. Age-related quality decline is the most common trigger. Queens age in specific, measurable ways. Their pheromone production declines across their reproductive lifespan, typically 2 to 5 years in well-managed colonies, but sometimes shorter in less optimal conditions. Their egg-laying rate peaks in their first 2 years and then progressively declines. Their sperm stores, accumulated during the mating flights of their first week of life, are progressively depleted as they lay fertilized eggs. And when the stored sperm runs low, the proportion of unfertilized eggs, which develop into drones, increases in ways that are measurable through cell inspection. Workers detect these changes through exactly the assessment channels described above. And as the queen's signals of quality decline below threshold, the colony initiates supersedure, the specific queen replacement process in which workers begin rearing new queens from young larvae while the existing queen is still present. Supersedure is a managed replacement process, in contrast to the emergency replacement response that follows sudden queen loss, and it typically results in the daughter queen being raised, mated, and beginning to lay before the old queen is eliminated. The elimination of the old queen in supersedure is often accomplished by the workers gradually reducing her access to food and grooming until she weakens and dies, or by the new queen killing her directly once she has mated, and is capable of producing fertilized eggs. The balling response, the immediate, violent elimination of a queen by heated cluster, is more typically associated with a different scenario: the introduction of a foreign queen. The foreign queen scenario is where the most dramatic queen rejection events occur. And understanding why workers respond to foreign queens with immediate aggression while accepting related queens through supersedure reveals something profound about the specific information the workers are using for their assessment. Queens produce colony-specific chemical profiles through their pheromone blends. While the major components of queen mandibular pheromone are broadly similar across colonies, the specific ratios and the additional components of each queen's chemical signature vary in ways that are colony distinctive. Workers calibrated to their own queen's specific chemical profile detect deviation from that profile immediately upon contact with a foreign queen. The evolutionary logic behind this recognition system is straightforward. A queen that does not carry the specific chemical profile of the colony is not the worker's genetic relative in the specific sense that the existing queen is. The inclusive fitness framework that makes worker sterility and worker investment in colony reproduction adaptive, the genetics that make raising sisters more fitness efficient than producing offspring directly, depends on the workers being accurate about which queen's offspring they are investing in. A foreign queen whose offspring would be less genetically related to the workers undermines the inclusive fitness calculation that justifies their reproductive self-sacrifice. Workers that accept a foreign queen without assessment would be investing their entire reproductive effort in raising offspring less related to them than the offspring of a same colony queen. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Selection strongly disfavors this, and the result is the hair trigger rejection response that beekeepers encounter when introducing new queens to established colonies without adequate management. The beekeeping practice of using introduction cages, devices that place the new queen inside a protected enclosure that the workers can access chemically but not physically, exploits this recognition system deliberately. Over several days of chemical exposure without physical contact, the workers become habituated to the new queen's chemical profile, updating their calibration of what their queen's chemical signature should be. By the time the cage is opened and physical contact is possible, the workers have partially accepted the new queen's profile as familiar, and the balling response is less likely to be triggered. This is, from the bee's perspective, a manipulation of the exact mechanism that protects against foreign queen acceptance. From the beekeeper's perspective, it is the practical application of understanding how the worker's queen assessment system works. Examine the laying worker problem because it represents one of the most dysfunctional colony states in bee biology and one that produces some of the most interesting queen acceptance failures. When a colony has been queenless for an extended period, longer than the few weeks during which emergency queen rearing would normally produce a replacement, the absence of queen mandibular pheromone allows worker ovaries to develop. Workers begin laying eggs. The problem: workers cannot mate, so their eggs are all unfertilized and produce only drones. A colony of laying workers produces only male bees, which cannot perform worker functions, and the colony's workforce rapidly declines without replacement from fertilized eggs. Introducing a mated queen to a laying worker colony is one of the most challenging queen introduction tasks in beekeeping because the laying workers have been producing pheromones of their own, including pseudo-queen pheromones from the most reproductively active workers that have become the colony's chemical reference state. A foreign queen introduced into this chemical environment is recognized as alien not just relative to the original queen, but relative to the new pseudo-queen pheromone environment, triggering extremely aggressive rejection responses. The laying worker colony has, in a specific sense, developed a new collective queen reference state around the distributed reproductive activity of multiple workers, and any single queen introduced into this environment is automatically rejected by this distributed reference. The colony has become its own enemy, committing to a reproductive strategy that will end the colony's existence while aggressively rejecting the one thing that could save it. This is where the evolutionary framework hits an edge case it was not designed for. The same mechanisms that protect against genetic infiltration by foreign queens. The hair trigger rejection of chemical profiles that deviate from the colony's reference state, become destructive when the reference state itself has become dysfunctional. The bees are doing exactly what their assessment systems are designed to do, and the outcome is the colony's destruction. Now address the swarm scenario, which is the queen replacement event most widely known to the public and the one that involves the most dramatic spatial dynamics. Swarming is the bee colony's primary reproductive strategy. The mechanism by which a colony divides, with the original queen departing with approximately half the worker population to found a new colony, leaving behind a new queen and the remaining workers to continue the original colony. Swarming is triggered by specific conditions, colony population reaching a density threshold, the lengthening days of spring triggering the reproductive impulse, and specific nest cavity conditions that signal the colony is approaching its productive limit. In the weeks before swarming, workers begin rearing new queens in the specific large vertical cells, queen cells that indicate queen rearing rather than worker or drone rearing. The queen herself usually does not intervene in the early stages of this process in ways that prevent it. The colony's collective decision to swarm is essentially irreversible once queen cells are present with developed larvae, and the old queen's options are limited by the worker's management of her activity during this period. The queen's response to the presence of developing queen cells varies. In some scenarios, she attempts to destroy the queen cells, inserting her stinger into the side of the cell to kill the developing queen before she can emerge. Workers typically prevent this by clustering around the cells and blocking the existing queen's access. The workers are, in this specific moment, protecting the developing queens against the existing queen's attempts to eliminate them, a direct reversal of the protective behavior they normally show toward her. This role reversal is not a defection or a betrayal in any motivationally loaded sense. It is the behavioral output of the same distributed assessment and decision-making system that drives all queen management behavior, now outputting a new set of behavioral directives appropriate to the colony's current state. The colony has decided to reproduce. The workers are executing that decision, including the specific subtasks of protecting the developing queens against interference from the existing queen. There is a dimension to queen rejection that connects to an ancient human parallel worth exploring: the specific relationship between chemical signaling, group assessment, and the management of leaders whose capability is declining. Bee colonies manage their central reproductive specialist through a system of continuous assessment, chemical monitoring, and coordinated response to declining quality signals. The system is ruthlessly functional. When the queen's quality falls below threshold, replacement is initiated without sentimentality, without consideration of past performance, and without any individual bee needing to make the decision alone. Ancient human communities managed their experienced elders and specialists, their healers, their navigators, their most knowledgeable hunters, through systems that were more emotionally complex but served related functions. The community's assessment of an individual's continued capability to fulfill their specialized role was a continuous, distributed process carried out through the accumulated behavioral observations of community members, shared through the social communication channels that maintained community knowledge, and producing community-level behavioral changes that reflected the aggregate assessment. The difference is that ancient human communities had language, memory, and the specific emotional complexity of human social relationships, which produced management of declining individual capability through social processes that were nuanced, contextually sensitive, and often deeply uncomfortable rather than chemically automatic and immediate. But the functional, parallel, community-level assessment of specialist quality triggering community-level behavioral changes in how that specialist was treated and resourced was operating in ancient human communities in ways that were not entirely unlike the distributed queen assessment process in bee colonies. Both systems solved the same problem. How does a community of many individuals manage the quality of the specific individuals whose specialized contributions are essential to community function? Bees solved it with chemistry and superorganism decision-making. Humans solved it with language and social cognition. The solutions look very different. The problem being solved is recognizably similar. Address what happens to the old queen after supersedure, because popular treatments of bee colony queen management often stop at the replacement decision without examining what follows. In supersedure, the old queen and the new queen coexist in the colony for a period, sometimes weeks, during which the colony's workers are managing both queens simultaneously. The old queen's resource allocation typically decreases progressively as the new queen's pheromone production increases and workers transfer their primary attention and feeding allocation toward the more productive individual. The old queen's eventual fate varies by circumstance. In some cases, she is eliminated by the workers through the balling response once the new queen has established reproductive dominance. In some cases, the new queen kills the old queen directly. In some cases, the old queen simply dies of the neglect that follows her resource allocation reduction. The specific outcome depends on the timing of the new queen's maturation and mating, the relative pheromone production of both queens, and the specific behavioral dynamics of the worker population during the transition period. What does not happen in any normal supersedure scenario is continued equal investment in both queens indefinitely. The colony's reproductive resources are concentrated through the distributed assessment process on the queen that the collective assessment identifies as the higher quality investment. The transition is managed, not necessarily cleanly or quickly, to the higher quality individual, and the resources that had been directed toward the lower quality individual are progressively reallocated. This is not cruelty. In the bee colony's evolutionary framework, there is no framework for cruelty toward the queen any more than there is a framework for loyalty to her. There is only the continuous optimization of resource allocation toward the signals that indicate the highest reproductive return for the colony's inclusive fitness calculation. The queen that produced excellent offspring and high pheromone levels for 3 years receives exactly the same assessment process as a newly introduced queen whose profile reads as foreign. Past performance does not accumulate credit in a system that operates on present signals. Now address what beekeepers have learned from understanding these dynamics and how that understanding has practical applications that connect back to the biological substrate. Modern apiary management is, in a significant sense, the applied science of exploiting and working with the bee colony's queen assessment system rather than fighting it. Experienced beekeepers who understand what workers are assessing when they evaluate queen quality can proactively manage queen replacement to prevent the colony from making replacement decisions at ecologically suboptimal times, can introduce new queens in ways that minimize rejection responses, and can read the early behavioral signals of worker-queen assessment activity before those assessments produce dramatic outcomes. The skill of recognizing early queen supersedure behavior, the specific changes in worker activity patterns around the brood nest, the specific early-stage queen cell construction that precedes committed queen rearing, the specific changes in worker behavioral profiles that indicate the distributed assessment has begun shifting toward replacement, is the skill of reading the colony's collective cognitive state before it expresses in the more visible and dramatic behaviors of actual replacement. This is a form of literacy in the colony's distributed communication system. The beekeeper who can read these signals accurately is intercepting the colony's decision-making process at a stage where management options are broader, where specific interventions can influence the outcome in ways that serve both the colony's biological interests and the beekeeper's management objectives. The specific interventions available depend on why the assessment has been triggered. If age-related queen decline has initiated replacement assessment, requeening, the managed introduction of a younger, higher-quality queen can be timed to coincide with the colony's natural replacement impulse, reducing the resistance to introduction. If the assessment has been triggered by a colony that has reached swarm threshold density, specific interventions that reduce crowding pressure, adding hive space, splitting the colony, can interrupt the swarm impulse before queen rearing has progressed to the committed stage. In each case, the management strategy is calibrated to the specific biological state the colony is in, based on understanding of what that state means for the colony's assessment systems, and what interventions will work with rather than against those systems. Here is the full picture of what the balling event at the beginning of this video represents. The workers surrounding the queen, vibrating, generating heat, executing the thermal elimination of the individual who had been the center of their colony's reproductive and chemical organization. They are not engaging in betrayal. They have no framework for loyalty or betrayal. They are executing the terminal output of a distributed quality assessment that has been running across thousands of individual sensors, integrating data from multiple information channels, propagating through the colony's chemical communication system, and converging on a collective behavioral state that requires specific action. The queen provided something insufficient. The workers detected the insufficiency through the specific channels that their evolution has equipped them to monitor. The colony's collective assessment reached a threshold. The behavioral directive changed. They acted. There is a specific clarity to this that is almost philosophically satisfying if you can set aside the horror movie optics of the event itself. The bee colony does not accumulate gratitude, does not wait past performance, does not consider the difficulty of the queen's situation or the external factors that might have produced her current quality level. It measures present performance against present requirements and responds to the measurement. The queen is replaced when she needs to be replaced. The colony continues when the replacement succeeds. Evolution built a system to accomplish this specific function, and the system works. What the system cannot do, what no amount of chemical sophistication and distributed intelligence can produce, is the compassion and historical awareness and contextual sensitivity that makes human management of declining individual capability so much messier, so much more painful, and sometimes so much more just. Bees are extraordinary, but they are not human. That distinction is worth knowing.